Okay. Hello, my name is Nirvana Cabatero. I'm a postdoctoral researcher at the University of Geneva, where I'm working in Teresa Marquez group and also in Patricia Paruk group. I would like to thank to the organizers for giving me the opportunity to speak about one of my projects today here. I'm really enjoying the workshop. It's been super nice to discuss with all of you. The talks are being super nice. And I'm also very happy because yesterday something happened to me, and it was the first time that something like this happened to me in a physics institute. And it's that I had to kiwi in the ladies' toilet, which means that we are not so few women here, which is very nice. So congratulations to the organizers. But okay, with that, I would like to speak about the theory of disorder elastic systems and how we can use this theory to study collective cell migration. The theory of disorder elastic systems is a quite general theory, and it allows us to study many diverse systems where we can define interfaces. And let me tell you, interfaces are everywhere. For many diverse systems, which could be super different in the microscopical level, with typical scales ranging from nanometers to kilometers, as for example ferroelectrics, ferromagnets, solids, colonies of cells, or a burning forest, we can find these emergent structures, which are called interfaces. And interfaces are part of our everyday life. And it's very important to study them because by just observing a small part of the system, we can extract information about what's going on inside the whole system. So an interface is defined like this. Here we have a colony of cells moving in a media. These are epithelial cells. And we can define the interface just as the boundary of the colony of cells. But as I said before, interfaces can be found in many diverse systems, and one of my favorite interfaces is the one that we can find in ferromagnetic systems. This is a ferromagnet, which means that it has an easy axis of magnetization. So in light gray, the magnetization, In light gray, the magnetization is pointing outside the screen, and in black, the magnetization is pointing inside the screen. And we can define an interface as the region where the magnetization changes smoothly from one direction to the other. But what tools do we have to study these kind of objects? Well, here, the theory of disorder elastic systems comes to the stage. To use this framework, we just need to define a function which describes the position of the interface as a function of the space. So this is a brutal but effective approximation. We're brutally simplifying the system in the sense that we are not considering any internal degrees of freedom that interfaces could have. This is a not too bad approximation because usually the width of the interface is orders of magnitude lower than the length of the whole interface. For example, in these two examples that I mentioned before, in the colony of cells or in the ferromagnet. But in order to use this framework, we have to assume two things about this function. This function should be smooth and univalued. So in that case, the dynamics of these objects called interfaces, it's the result of the competition of the elasticity that these objects could have. We could also have some pinning or disorder. It's also the result of the competition of an external force that could be applied to the system. In the case of a ferromagnet, this external force could be an external magnetic field, for example, and also the temperature. So this is very nice, and it allows us to obtain very precise exponents describing the statics and dynamics of the system. But we have a problem. This is a real interface. And the thing is that real interfaces do not always behave very nicely. So this is a ferromagnet, and we can see some things as bubbles, overhangs, or strong pinning centers, which cannot be captured by the framework of disorder elastic systems. So our approach was instead to use order parameter to describe the state of the system. So instead of just describing the interface, as a one-dimensional system, as before in the framework of disorder elastic systems, we decided to model the state of the system with this order parameter. So this order parameter is representing the state of the system. And to describe the dynamics of this order parameter, we used a Ginzburg-Landau approach, which is very similar to the one used by Julia and Christina. But here is different. Here we are modeling the state of the system. So this order parameter would like to have two preferential values. In the case of a ferromagnet, this could be the projection of the magnetization along the easy axis of magnetization, which means that, for example, the magnetization pointing in one direction corresponds to one minima of the order parameter, and the projection of the magnetization in the opposite direction corresponds to the other minima of the order parameter. Or if we have a colony of cells, this could represent the cells that we're inside the colony or we are in the media. So we consider this double well potential to mimic this preference of the order parameter of having two preferential states. We also consider exchange, and this is a non-conserved order parameter, which means that the simplest equation that we have to describe its dynamics is a Langevin equation. So we solved this equation numerically, which is a highly non-trivial task if you want to study large systems for long times. But we developed our own code in CUDA C++, and we did the simulations. And the good thing is that with this kind of approach, we can really capture some features of real interfaces. For example, we can see overhangs. We can also model strong pinning centers, and a very important thing is that here we can study nucleation, which is a feature that cannot be captured by the one-dimensional description. So with this model, it's not easy to do so many analytical calculations, but still we can do some things. For example, we can compute the elastic energy of an interface in this two-dimensional model. And how we can do that? Okay, we can compute the energy of a system with an interface, which means that the order parameter here takes one value of the minima, and here takes the opposite value, the value on the other minima. And we can compute the energy of this system, subtract the energy of a system without an interface, which means that the order parameter only takes one value along the whole system, which gives us the elastic constant per unit length that this interface will fill. I will omit all the calculations, but it's also possible to find which is the relation between the friction felt by the interface in the one-dimensional model and the friction felt by the interface in the two-dimensional model. So at first, we thought that to connect the one-dimensional description with the two-dimensional description only with elasticity would be enough. But no, you also need to rescale the friction. So the friction felt by the interface in the two-dimensional system is related with the friction felt by the one-dimensional system with some simple relation of the parameters. So to test the connection that we did with both theories, so we were able to connect the one-dimensional theory of disorder elastic systems with this more general theory in 2 dimensions. But to test that the connection that we did was good, we measured, for example, the roughness. We measured different observables, but this roughness is something that I like very much because it allows us to extract a lot of information about the system. So the roughness is defined just as the correlations in the height of the interface at different positions. So we can start, for example, in the one-dimensional model with a flat interface. We let the system evolve, and since this system will evolve as the result of the competition of elasticity and temperature, here we are not considering disorder yet, this interface will become rough and rough when the time passes. And we can repeat the same experiment, the equivalent experiment in the 2-dimensional system. So we start from a flat configuration, which means that here the order parameter takes one value, and here the order parameter takes the other value. We let the system evolve. And since, again, here how the order parameter evolves depends on the competition of all the energies that we have in the system, the interface will become rougher and rougher when the time passes. The good thing about this quantity is that if we start from a flat configuration, we can use, for example, the Martin-Sijarros formalism to compute analytically how this quantity will behave, which takes a lot of equations, of course. But it allows us to obtain a function which depends on the parameters of the system, which describes how this roughness, these correlations in the interface will evolve. So we did simulations in the one-dimensional model. Of course, in the one-dimensional model, we are already simulating how the interface will behave. So we have the position of the interface at each point in space as a function of time. But when we do the simulations in the two-dimensional model, we don't have the interface. So we developed a criterion and an algorithm to detect the interface. So we detected the interface in the two-dimensional system, and we followed the evolution of the interface as a function of time. And we measured the roughness. And what we found, here are the results for the one-dimensional system, and here are the results for the two-dimensional system. And we found a very, very good agreement between the analytical results, which are plotted in different color for different times in dashed lines. We did 10 different realizations for each simulation. Here is the average over 10 different realizations at each time. And the coincidence between the one-dimensional model, the two-dimensional model, and the analytical results, it's excellent, which proves that the connection that we have between both models is working very well. But now, of course, we are interested in studying how a colony of cells is moving. So we used this framework. We analyzed colonies of cells moving as a function of time. You will hear more in the next talk. Guillaume did the experiments. And we followed the evolution of a colony of cells as a function of time. And for each time, we measured the roughness as a function of the distance. And we were able to extract very useful information. And you will hear more about this later. So to conclude, I would like to just recall that we were able to connect the one-dimensional model with the two-dimensional model. This is super useful because now we can use all what we already know about the one-dimensional model and extend it to the two-dimensional Ginzburg-Landau model. And so we checked this result by simulations at the two levels. And we also show that the roughness in the 2D and the 1D model are very well described by analytical results. And this is super important because now we have a tool to develop new observables to study interfaces. And with that, I would like to thank all my collaborators and my founders. Thank you very much.
Maybe just answer from this.
I enjoyed that. Could you say a little more about the friction and how that enters the analysis and what it means in this context?
Yes, sure. So we have two models. We have the one-dimensional elastic system. Here, the friction is on the equation on your left. And it enters into the temperature, how the temperature acts in the system. So this friction is, the correlations in the temperature are proportional to the friction in the one-dimensional model, and also in the two-dimensional model. So the temperature in both systems is the same, but the friction has to be rescaled. In the sense that...
Is that like a fluctuation dissipation
yes,
theory?
Yes, and to satisfy this and have the same temperature, the equivalent temperature in both models, you have to rescale the friction. That's it.
What would change if your other interfaces or your other side is not a passive medium, but another active system that's actively pushing back?
Sorry, can you repeat?
If you have two tissues that are interacting, or you have some non-trivial medium as the second side of the interface, like something that isn't just free space or an elastic medium, and you have pressure back and you have active changes along that interface.
Well, yes, I think in that case you need to consider, for example, some more general model as Julia or Christina did, where they are considering two phase fields. Here it's only one phase field model. And of course, the thing will change a little bit, or a lot. Well, actually, that is what they are studying.
I guess what I was wondering is there a way to sort of ignore the complexities of the phase fields and just knowing that you have two things pushing on either side of an interface and just looking at the interface, find
Well,
something
yes,
meaningful?
that's the whole point. Is that
Right.
that's the whole point of this? Yes.
So even if neither side, or if both sides are complicated, you can still ignore those complexities.
Yes. Yes, that's the
Nifty.
idea.
Terrific. Let's thank Nirvana.